Welcome back to A-Star Tuition channel. Today we will talk about dynamics part 1. Let's get started. Last time we learned about kinematics, which is aspect of mechanics that deal with motion without focus on the cause of motion. Now let's start with the discussion of dynamics. Okay, so dynamics is really part of mechanics that deals with the cause of motion. Now, at the center of dynamics is Newton's law of motion. Now, let's start with the notion of Newton's law of motion, and then we'll see some example. Now, let's start with Newton's law of motion. There are 3 of them. So, the first Newton's law says sigma F equals 0, which means that the resultant force equals 0. So what does it mean? It means that when an object has no resultant force, or the resultant force is 0, then the object will experience no acceleration, which means that the state of motion remains the same. Now what it means by state of motion is that whether an object is moving with a constant velocity or that the object is at rest. Now, so then with this we actually have 2 distinctions. So we say that an object that has acceleration equal to 0 and velocity equal to 0, that means that the object is in static equilibrium. So the resultant force is 0. So the fact that the resultant force is 0 means equilibrium. Yeah, but then it's a static one because the object is at rest, not moving. On the other hand, when the velocity is constant but non-zero, then we are dealing with what we call as dynamic or kinetic equilibrium, meaning that the resultant force is still 0, but then the object will keep maintaining its velocity as long as there is no force applied to the object. The second law is resultant force is equal to mass times acceleration. So that when the resultant force is non-zero, it is numerically equal to the product of the mass and its acceleration. Now, please understand that mass here is a scalar, acceleration is a vector. So resultant force is a vector that is in the same direction as the acceleration, because mass is always a positive quantity. And also, please bear in your mind that this aspect of Newton's law of motion works for constant mass. When the mass is not constant, later in part 3 of the video, we'll discuss or we'll revisit the second law when the mass is not constant. For the third one, it says F action equal minus F reaction, which we can say as for every action there's always equal and opposite reaction. So for instance, if you have one object exerts a force on another object, let's say object A exerts a force on object B. Now the reaction is that the B will also exert the same amount of force to A, but with the opposite direction. So that's action and reaction. Now, as you can see, this law is very much related to the notion of conservation of momentum, which we will also discuss in the third part of the video. Now, when we talk about Newton's law of motion, as you can see, we deal with forces, right? So in mechanics, there are actually type of like mechanical forces that you need to be familiar with, because these forces will appear almost ubiquitous, in not just mechanics, but then later when you learn other branch of physics like electricity or waves. Now, the first one is weight. So weight is simply put, if you have an object that has mass, like for instance this marker over here, this marker, it has its own mass. Now if you do not hold the pen, so what happens is you can guess that the pen will fall downward. Now the reason for that is because of the gravitational pull from the earth. So weight is actually the gravitational pull on an object that is bound to a certain large concentration of mass. Now what I mean is, for instance, our earth, so because we are all earthbound, then object on earth will be pulled by the earth, and the amount of pull is called the weight or the gravitational force. Now if you are at a certain location above the surface, from the sea level to a certain location, this quantification of weight is actually uniform. What I mean is that you can actually use the formula mass times the gravitational acceleration at the surface of Earth. Now the value of the gravitational acceleration at the surface of Earth will be the same for at the location on the ground up to about 1 kilometer above. So the value doesn't change that much, so we can assume it to be uniform. But if an object can be brought to a vertical location much above 1 kilometer, then the value will be different, it will be less. But for everyday discussion, we tend to assume that objects are located relatively at small altitude, so small vertical distance from the ground, and the value of g, which can be different from place to place, location to location on Earth, but the accepted value is 9.81 meter per square second. Now this is actually equivalent to Newton per kilogram. So whatever the mass of the object, you multiply by this value, it's going to give you the weight. Hopefully you understand the idea of weight. Next one is normal or contact force. So when two objects are in contact with the other, like this, so let me illustrate here. Let's say that this is a table, okay, and above the table you put your book above the table. So the book here will experience a contact or normal force. The reason why we call it normal, because it's perpendicular to the surface. So there's a normal force acting on the book. Now, how do you know there's a normal force? Well, if there is no normal force, then the weight of the book will allow the book to free fall, to reach the ground. But then, because of the normal force, then the weight is balanced by the normal force. So normal force itself is not, you cannot really, there is no formula actually for normal force, but you can always find the value of normal force by analyzing the force diagram. Now we will talk about force diagram later. Next is tension in a taut string. So when you have a string, it could be in a slack condition like this, or it could be in taut condition like this. Now when a string is in taut condition, there is a tension acting at each part of the string. So if, let's say, you have an object, let's say a block that you tie with the string, and then you apply a force to the string, then what happens is that there is a tension acting on the object. So remember, every time you have a taut string, there is a tension. Okay, so the next one is a general push or pull force. So object could be pushed or could be pulled by someone so that the object accelerates with a certain acceleration, or perhaps to maintain the same velocity. So in general, we do not distinguish between push and pull, so this is just applied force. The next one is the elastic force from extended or compressed spring. Now when you have an elastic spring, and then if you attach that one end of the spring to another object, then if the spring is stretched or compressed, then the spring can actually exert an elastic force to the object that is attached to it. So for instance, we see that this object is attached to a spring that is compressed. So someone is compressing the spring. So what happens is that the spring is actually exerting a force, the elastic force, to the object. Now we can quantify that by using Hooke's law, which is F equal to minus kx, which means that the amount of elastic force is proportional to the amount of extension or compression of the spring. So if the spring has a natural length of L, and then you either extend it by x, or if you compress it by x, then the amount of force is equal to a constant times x. Now this constant sometimes is called stiffness or the spring constant. So let's call it, so this is the stiffness or spring constant. Now you can see that F is force, so we measured in Newton, X is in meter, so K has a unit of Newton per meter, or Newton meter to minus 1. So let's say for instance, if a spring has a value of K equal to 500 Newton per meter, it means that in order to stretch or in order to compress the spring by 1 meter, a force of 500 Newton is required. Now once you release that, then the spring will exert the force to the object. Last, let's talk about frictional force. So when you have an object, let's say you put the object on top of a floor. If the floor is rough, it has a rough surface, then when there is a relative motion between the object to the floor, let's say that someone is trying to push it so that the object will slide across the floor, then frictional force will come into existence. So it applies to surfaces that is rough. Now, if the surface is slippery, sometimes you can simply ignore because the value is too small. But in a lot of cases, you cannot ignore it. So let's discuss. So here, as you can see, when an object is of a certain mass is pushed, then what happens is that initially it will be tough for the object to move, even though a force is applied to the object due to friction. Now, to give you a better example, let's imagine that you have a refrigerator, and then the refrigerator is on top of a rough surface, and that someone is trying to push the refrigerator so that it can move across the floor. Now, imagine that the amount of force given is initially 1 Newton. And what happens is that the refrigerator is not moving with this force. So what happens is that if it's not moving, initially it's not moving, now it's still not moving, so there's no acceleration, which means that the resultant force is 0. Now, but then we know that there's a push here, 1 Newton. So if there's a push of 1 Newton, how come the refrigerator doesn't move? So we can only conclude that is because a frictional force is now comes into existence, and the value is exactly 1 Newton, and it's acting on the opposite direction. So there's a result, there's a frictional force of 1 Newton acting on the refrigerator. So now the resultant force on the refrigerator is 0. Now, so 1 Newton is not enough. So the person then tries to increase to 2 Newton. And it turns out that the refrigerator is still not moving. So what happened? Again, 2 Newton not moving means that the acceleration is still 0. Yeah, actually, the acceleration is 0 because initially it's not moving, and now it's still not moving. So we say that the acceleration is 0. That means the resultant force is 0. But then the force given is 2 Newton. So we can conclude that actually now the frictional force has increased its value to 2 Newton. So you can see that the value of the frictional force is not constant. Now you can see that the value will follow whatever the force applied to the refrigerator. Again, increase to 3 Newton, still not moving. That means now the frictional force has changed its value to 3 Newton. In fact, if we were to sketch a graph of frictional force versus applied force, we can see that the value of the frictional force and the applied force are the same so far. Yeah. So in fact, the line is going to be a straight line in which the value of frictional force is exactly equal to applied force. However, this is not going to be like this forever, because if there is enough force that you apply to the refrigerator, then the refrigerator will move, or will start to move. Okay, so let's say that you increase to 10, still not moving, so that means the frictional force is now 10. Okay, now then you increase to 15 Newton, still not moving, so that means the frictional force is now 15 Newton. But at 15 Newton, it could be that the refrigerator is on the verge of moving, so it's about to move. So that means in this case the 15 Newton is in this case 15 Newton is the maximum static frictional force. Okay, so this is the maximum static frictional force, which means that this is the friction when the object is still not moving. Yeah, so that's why we call it static. But then it's maximum value. Now, when it reaches its maximum value for the static frictional force, it means that if we were to increase this value to a higher value, let's say now we increase to 16, what happened is that the object will start to move. Now when the object starts to move, that means that it's no longer in static state, so it's moving. Now when it's moving, the friction, the friction is called kinetic friction or dynamic friction, and that dynamic friction or kinetic friction have a constant value, and the value is actually less than the maximum static friction. So this over here is the dynamic or kinetic friction. So it's the friction, the frictional force acting when an object is moving or in the state of motion, right? Now the value is less than the maximum static friction. Now, based on experiment, the value of the maximum static frictional force can be calculated by using the formula, the normal force multiplied by mu s. Mu s here Okay, let me write down. So this is the normal force, and mu s is the coefficient of static friction. Now the value depends on the nature of the surface. Yeah, so rough surface, even rough is not, single state. You can have a gradually, rougher, less rough, and so on. So this value is not something that you need to know for surface, because each surface, each situation is different. And then for the kinetic friction or dynamic friction, the value can be calculated by N on the normal force multiplied by mu d, or again here N is the normal force and mu d is the coefficient of dynamic or static or kinetic, dynamic or kinetic friction. The value of mu s is always always greater than the value of mu d for the same surface. As you can see here, because of this fact, the value of dynamic or kinetic friction is always less than the maximum static friction. Now please understand that this is the maximum static frictional force, which you can calculate by using this. However, if a static frictional force hasn't reached its maximum value, do not calculate by using this formula. So a lot of misunderstanding from students is that they always use this formula to calculate the static frictional force. It's actually not correct, because you can only use this formula to calculate the maximum value of maximum value of static frictional force. Now, in fact, we can write the equation or the inequality as this: Fs is always less than or equal to Fs maximum, which is equal to N times mu s. So how do you calculate static frictional force when it hasn't reached its maximum value? The answer is just look at the applied force. Whatever the applied force is, that value is equal to the value of the static frictional force. Yeah. Hopefully you understand the idea, and that you can apply it in all situations in mechanics that is related to friction, or in which the friction cannot be ignored. Now let's talk about force diagram or free body diagram. Now, in order to solve a problem in mechanics, we sometimes need to draw a force diagram to see what forces acting on an object, and then try to analyze the forces by using methods of resolving the factors. Because remember, force is a vector. Now, let's say, for instance, an object that is, you apply a force F, and this is theta over here. Yeah. Now, let's say that the object is already in motion, but that there is a friction. Now, in this case, the friction is the dynamic friction or kinetic friction, because the object is in motion. So this is Fd. Yeah. Now, you can see that there are also normal force acting here and weight. Now, normally, or in a situation when there is no pulling force like this, let's say that an object is stationary on top of a table, the normal force is equal to the weight, yeah, because the resultant force 0, so you can see N minus W 0, so N equal W. But then in this case, the N is not equal to W, and the reason is because there is a component of the pulling force that contributes to the upper direction of the force. Now you can see that this force F over here, you can resolve. Remember, we learned about resolving vector. We can resolve to F cos theta. and vertically we can resolve to f sine theta. Now, as you also remember, after we resolve into components, we need to look at the resultant vertical component and the resultant horizontal. Let's look at the resultant vertical. Now, for the resultant vertical component, you see that there's n upward, and then f sine theta also upward, and then w downward. Now, if the object is moving to the right, then we can see that the object is constrained to move on the surface. So constrained to move on the surface, so mean that it never leaves the surface. If it doesn't leave the surface, you can see that it doesn't move vertically up and down. So the resultant force in this case is 0. So we can say that, okay, normal force equal to W minus F sine theta. Now, on the other hand, the resultant sigma Fx, or the sum of all horizontal forces, as you can see, it consists of F cos theta. Now, F cos theta is directed to the right, yeah, so F cos theta. And there's friction, but friction is always against the motion, yeah. So it's always against the motion or against the tendency of motion. So minus Fd. Now in this case, if the object is moving and that this value is greater than this value, then we say that it's accelerating, yeah. Remember, sigma F equal to ma. Now how do we quantify Fd, or the dynamic friction? Well, the dynamic friction is equal to the normal force times mu d. Now, mu d is usually a quantity that is given. Now, the normal force here is given by this. Remember, we solve for the normal force. So then we can just substitute the value here to find the dynamic friction. So the N, or the normal force, is weight minus F sine theta times mu d. So then here we can say that, okay, F cos theta minus Fd, which is W minus F sine theta times mu d, equal to ma. Yeah. So here we have F cos theta minus, remember, weight is mg, yeah, so this is equal to mg times mu d, okay, and then plus F sine theta times mu d equal to ma. Now if you want to calculate the force, the pulling force, then what we need to do in this case is to isolate F, yeah? So make F the subject, so F cos theta plus mu d sine theta, and this is equal to ma plus mg times mu d. Yeah, so then from here we can say that the amount of the pulling force is equal to m a plus g times mu d, the whole thing divided by cos theta plus mu d sine theta. So it all depends on what the question is asking for, whether to find the force or to find the acceleration, depending on what is given and what is asked. So what is important is that you know how to use free body diagram to resolve the factors into components, and then solve for the resultant force in each component. Like for instance, this one is the resultant force in the vertical component, and this is in the horizontal component. Now, in addition to dealing with situation in a flat level surface, we sometimes deal a lot with inclined plane. And so you have like inclined plane or ramp like this, and an object is put on top of it. Yeah. Now, in the case of object in inclined plane, there is actually a slight different way to deal with it, which is we do not resolve it in the direction of the norm or the regular horizontal or vertical. Now remember, the regular horizontal is this, yeah, sideways, and the regular vertical is this, yeah, up and down. However, in an inclined plane, there is an inherent advantage to deal with the problem by resolving the factors in the axis that is parallel to the plane and perpendicular to the plane. So this is the axis that is parallel to the plane. So this is the parallel axis, and we also have the perpendicular axis. So this is the, now remember that these two axes are perpendicular to each other. So this is the perpendicular axis. So then all forces in this situation will be resolved in the direction of parallel or perpendicular, yeah, not the normal sideways or up and down, okay, for inclined plane. Now let's say that the inclined plane makes an angle of theta with respect to the horizontal plane, yeah, or the horizontal axis. Now, and we assume that the object is constrained to move within the plane, meaning that the object never actually leave the plane. Now, if the object never leave the plane, that means the sum of all perpendicular axes, yeah, will always be 0. So in this case, there is a normal force. Oops. Remember, the normal force needs to be perpendicular, yeah, to the surface. Okay, so this is perpendicular to the surface. This is the normal force. Okay, so normal force. And there's also the weight. Now, so the weight is, you know, that is always vertically downward. However, as I mentioned just now, we usually resolve this, all the forces in the axis, in the parallel axis and the perpendicular axis. Now this angle over here is also theta, yeah. So if this is theta, and this is also theta. Now this is you can easily prove it, yeah, if you learn about property of angle in geometry, for instance. Now if this is theta, this is theta. Now weight is equal to mg. Now if we resolve the mg in the parallel axis, what you will wind up is you will wind up with this, yeah. So this is mg sine theta. So this is the component of the weight, yeah, that is parallel axis, and you can see that the direction is down the plane, yeah, down the inclined plane, downhill. Now on the other hand, if you resolve it in the perpendicular axis, you will wind up with this, and it's directed perpendicularly into the plane, and it's mg cosine theta. Now remember what I just mentioned earlier, that if the object is to never leave the surface or is constrained to move within the surface, then the sum of all forces in the perpendicular axis is always 0. So then sigma f perpendicular consists of normal force, or n, minus mg cos theta, and this is equal to 0. So in this case, the normal force is equal to mg cos theta. Now please understand that in inclined plane, it's equal to mg cos theta, but it doesn't have to always be equal to this. So if you have any additional forces that when you resolve in this perpendicular axis, it can add up to this, yeah. But then as long as the object is constrained to move within the plane, then the sum of the perpendicular force will always equal to 0. So that's the starting point. Now for the resultant force in the parallel direction, you can see there's only one force, and this is unbalanced, mg sine theta. Unbalanced means that there is no other force that counter it, meaning that in the minimum configuration, yeah, in the minimum configuration, the object that you put on top of a inclined plane will always slide down. And the amount of acceleration is equal to, remember, sigma f equal to ma. So the acceleration is always g sine theta. So it will always slide down. Now, unless there are other forces, like for instance friction. Now, if there's a friction, remember the friction always against the direction of motion, or the direction of the tendency of motion. So then, if the tendency is to slide downward, then that means there has to be a force, or frictional force, acting in the opposite direction. But then, a minimum configuration meaning that if we neglect friction, then the object will always slide down. Let's talk about terminal velocity. Now, in the video of kinematics, we discussed a bit about vertical motion. Yeah, so a particle is subject to its own weight. So therefore, it will accelerate uniformly downward. Now, this is probably useful in everyday situation in which you drop something from a vertical distance that is not too large. Let's say, an apple, or maybe like you have a small rock that you drop and it hits the floor on the ground. However, if the object is taken to a large enough vertical distance, like on top of a building or maybe on top of a mountain, then the object usually will be subject to what we call as air resistance. So that in addition to the weight of the object, there's air resistance. So F, air resistance. Now, air resistance usually depends on the speed or the square of the speed. So we say that it's proportional to the speed, or speed square. So it's a function of how fast the object is moving. Now, initially when you drop, there is no speed yet. Now, it will gain speed as it moves downward. As the speed increases, so does the air resistance, because remember, it's proportional to the speed or the square of the speed. So what happens is that this force acting on the object will decrease the resultant force. Because remember, here this is the force diagram, so we can write down the resultant force as mg minus, let's say, kv, a constant times v, and this is equal to m times a. Yeah. Now, the difference between this equation than other equation that we encountered previously is that this one cannot be easily solved because the phi here depends on a. So there is like explicit relation, actually internal relationship between a and v. So you cannot just solve it. But luckily, this is actually not difficult to solve if you understand calculus. So let me just quote you the result, yeah, rather than discussing the calculus itself. Yeah. So what happens is that the velocity as a function of time will look like this. So it has some exponential behavior, decay, exponential decay. So the equation will look like approximately phi equal to phi m, where m is the max, phi t times 1 minus exponential minus something. So it has this form, yeah? But again, this form is actually not important for you to know. What you need to know is how it behaves. It behaves like this. So the graph is going to look like this. So that eventually, when the speed increases, okay, so as I mentioned earlier, it has weight, but there's no air resistance yet because the speed is 0 initially. Now, as it gains speed, this will increase, but then this is fixed. So as time goes by, you should expect something like this for the net force. Yeah. See, look at the force that is downward, the weight. The weight is always constant, but then the air resistant force increase because again the speed increases. Now at one moment, at one time, the value of the air resistant force will equal to the weight. So that when that happens, the resultant force, when mg minus kv is the same, the resultant force will become 0, and from there we can solve for, when that happens, we name the velocity as Vt, and Vt is equal to mg over k. Now this Vt here is the terminal velocity. Now why is there terminal velocity? Because remember, once the air resistant force has the same exact value as the weight, then the resultant force becomes 0. Remember, when the resultant force 0, what is also 0? The acceleration. So once mg, which is the downward force, is equal to kv, the resultant force equal to 0, and when that happens, the acceleration is also 0. When the acceleration is 0, what does it mean? It means that the velocity doesn't increase any longer. So it will reach this value, which is called the terminal velocity. So remember, this usually is related to when you drop something from a vertical position that is large enough. Yeah. Or now in most cases you can just ignore it, but if a question make a reference to either a high position, large building, or maybe they explicitly mention that air resistance is non-negligible, then please pay attention to the notion of terminal velocity. Okay, so that's it for today's video about dynamics regarding forces. We'll continue our discussion in the second part of dynamics lecture, which is about work, energy, and power. I hope you enjoyed this video and hopefully it's helpful. Don't forget to like, subscribe, and share this video. I'll see you again next lesson.